Hello again, my name is Tom Irvine and I'm the instructor for the series of shock and vibration webinar units, and I express gratitude to the NASA Engineering and Safety Center, NESC, and to Dr. Curtis Larson for making this series of webinars possible. The topic for today is the Power Spectral Density function, the PSD. And what we found out in one of the previous units is that a Fourier transform by itself was a rather poor format for representing random vibrations such as white noise. And the reason is because the Fourier magnitude depends on the number of spectral lines, and the number of spectral lines depend on the duration. So if we take a very long, some arbitrarily long time history and take a Fourier transform of that, we would get a high density of spectral lines, and the corresponding amplitude of those spectral lines would be relatively low. But then if we took a shorter time history and took the Fourier transform of that, we'd have a fewer number of spectral lines, and thus the average magnitude of those spectral lines would be higher. And this is assuming that we have stationary broadband random vibration. So we need a method for overcoming that limitation, because we need something that we can design and test for as engineers. And if the Fourier transform magnitude depends on duration, then the Fourier transform itself is not suitable for coming up with a level for design and test purposes. But the power spectral density function, which by the way can be calculated from a Fourier transform, overcomes this limitation. And there's many characteristics of the power spectral density function, and let's just start with one here. The power spectral density function is going to represent the magnitude, but it will discard the phase angle. Now, when we were doing our Fourier transforms and fast Fourier transforms in previous units, we came up with plots that showed both the Fourier magnitude as well as the phase angle. And we typically would just cancel out of that plot and only look at magnitude only for Fourier transforms. Well, there are some cases within Fourier transforms, within vibration testing, I should say, where phase is important. For example, if we're doing modal testing, that's M-O-D-A-L, modal testing, phase angles are important. And then there's some other situations as well in which phase would be important. But for the type of testing we do on shaker tables, when we have avionics components and we mount them on shaker tables to apply a base acceleration, the phase angle is not important in that case. And that actually gives some leeway to the test technician or test engineer in the control system, because once we specify a power spectral density test specification, then the test engineer, the test conductor, has to meet that magnitude, but can use any phase angle whatsoever to satisfy that in terms of the phase angles of the individual spectral components. Okay, so what else here? The magnitude for power spectral densities is typically represented as g squared per hertz. Now, when we say g squared per hertz, that is really g RMS, so the g root mean squared per hertz. So g RMS squared per hertz. But just as for brevity, that's typically simplified to g squared per hertz. Now, there's two types of power spectral densities we're going to be dealing with in this and several upcoming webinar units. And one is going to be a power spectral density as expressed as in a test format, a test specification. Then we're also going to look at power spectral densities of measured data, or in some cases we're going to have synthesized data where we make up our own data and take a power spectral density of that. Now, what I'm showing in this plot is actually a case history. This is an actual test specification that comes from a Navy document called NAVMAP P9492, and I think we took a look at that document in a previous webinar unit. But this is right out of that test specification. right, it's a test specification right out of that reference. So what we have here is a couple of things to note. It's a log-log format, so both the y-axis and the x-axis are in logarithmic form. Now the y-axis has g squared per hertz. Well, really that's GRMS squared per hertz, but it's abbreviated g squared per hertz. Then along the x-axis we have frequency in hertz. And an important point that I want you to start thinking about, this hertz here along the y-axis, the hertz in the denominator of the unit for the y-axis, that hertz there, it's best to think of it as being separate from this hertz in the x-axis. Because what this hertz here in this y-axis unit denominator, what it really represents is a bandwidth, a small, narrow bandwidth. So think of this narrow bandwidth as being, it could be 1 hertz, it could be 5 hertz, whatever, some small, relatively small frequency. And what we're doing is we're calculating the GRMS level within each band, and we're squaring that. And really you can think of the GRMS squared as being like the variance. Now the variance is the standard deviation squared. And the reason I'm saying this is because the mean value is going to be 0. So we can interchangeably use GRMS and standard deviation. Those two values are the same if we have the mean value equal to 0. So the GRMS squared represents the amount of energy within a particular narrow band which has a bandwidth of maybe 1 hertz or 5 hertz or some number thereabouts. So start to think of a PSD in those terms. Okay, so what else do we have here? Several other things to note. This specification goes from 20 hertz to 2000 hertz. Now, this would be typical for testing electronic components and equipment that would later be mounted on a launch vehicle or a rocket vehicle of some sort, or maybe an aircraft. And it's the level, the test specification, it starts at 20 hertz. And there's two reasons for that. One is there's a desire to avoid the low frequency displacement. So at low frequencies we can get very high displacements, and those could potentially exceed the stroke limit on the shaker table. So typically, at least for aerospace, these specifications begin maybe at 10 hertz or 20 hertz. Now, there are, of course, exceptions to that, and particularly if you go to military standards like 810, for example, and those sorts of standards also have levels for ground vehicles and helicopters and all sorts of other military type equipment. Transportation levels, for example, for equipment that has to be shipped in a semi-trailer, possibly over rough roads. So for those mil standard 810 types of power spectral density specifications, some of those do go down to 5 hertz or so. But we always have to be concerned that there's a potential for high displacements at low frequencies. Now, another reason we go from 20 to 2000 hertz for aerospace is typically we're concerned about circuit boards in electronic boxes. And those circuit boards tend to have frequencies, for the most part, fundamental frequencies anyways, that fall from, say, 200 to maybe 600 hertz or so. That's where probably 95% of electronic boxes have their fundamental frequencies. Now, are there outliers? Are there exceptions? Yes, there are. But if we test from 20 to 2000 hertz, that's going to represent the energy fairly well that's capable of exciting that fundamental mode on that circuit board in that electronic box. Now, having said that, not all avionics components have circuit boards, and there are other things. There are various electromagnetic and pneumatic and other types of equipment as well. But anyways, going from 20 to 2,000 hertz has served the aerospace industry well for many years, at least for the launch vehicle part of the aerospace industry. Okay, couple other things we need to look at here. Now this is a case history. This is an actual published spec. When we look at this spec, we can see, okay, our first coordinate is at 20 hertz, and that has an amplitude of 0.01 g squared per hertz. That's pretty easy to pick off that breakpoint. And then the specification shows a slope. It's plus 3d per octave. Then the specification reaches a plateau from 80 to 350 hertz, and that plateau is 0.04 g squared per hertz. And again, that g is really GRMS. So it's really GRMS squared per hertz. So we have the flat plateau. Then starting at 350 hertz, there's a downward 3 dB per octave slope. And as we look at the specification, it's not really clear where this final breakpoint magnitude is. We can kind of count the ticks and estimate it, I guess, but the specification did not directly say what the last g squared per hertz level would be for that final breakpoint. So we're going to do that as a little in-class exercise here and figure out how to calculate that last breakpoint. Now also there's something called the overall GRMS level. And the overall GRMS level is equal to the square root of the area under this curve. And when we do that integration to calculate the area, we cannot use your simple geometrical relationships that you may have learned in high school. We cannot, for example, take a triangular section and say, oh, the area is 1/2 base times height. And the problem is we have log-log format. So when we have a log-log format, the integration becomes more complicated. The equations for these lines, but these line segments become more complicated, at least for the two sections that have slopes. So we're going to have special integration rules. And one of the things I want to encourage you is anytime someone gives you a power spectral density specification, of course the GRMS should also be explicitly stated, but it's a good idea to double check and go ahead and take the square root of the area under the curve and compare that to the GRMS value just to make sure all the numbers line up. So it's a good cross check. Now, 99% of the time when someone gives you a PSD curve, the GRMS value will be correct. But for every 1 out of 100 times when it's incorrect, that's something that you want to know, so you can figure out if there was a typo error or a miscalculation or something. Again, the overall GRMS levels, what it really is, it's like taking this power spectral density curve and reducing it to a single value. And in some sense, it represents the severity of the input level. But obviously there's more to the story because we're also concerned about how this energy is distributed with frequency. And then the next step of concern is, well, what is our natural frequency of our piece of equipment that will be tested to this PSD? And also, just as a reminder, this PSD is intended as a base acceleration or a seismic acceleration of the equipment. We can also take PSDs of force or pressure or displacement velocity or voltage or just about anything else you can measure. But most commonly when we're dealing with PSDs, we're dealing with acceleration for design and test purposes. Okay, so our next task at hand is, let's go back to our NavMat P9492 random vibration power spectral density. So you've seen this plot before. So the task is to calculate this last breakpoint magnitude. So the first thing we need to do here, the next thing, is to calculate the number of octaves. So from 350 Hertz to 2000 Hertz, how many octaves do we have? And you should recall from a previous sine sweep unit that if we take the natural logarithm of the upper frequency, and that upper frequency in the argument is divided by the lower frequency, take the natural logarithm, divide by the natural logarithm of 2, that's the number of octaves. So from 350 to 2000 Hertz, there are 2.51 octaves. And just as a review, an octave means a doubling of frequency. So we have a minus 3 dB per octave slope there. So the level change from 350 to 2000 Hertz is equal to minus 3 dB per octave times 2.51 octaves, and that is equal to minus 7.53 dB. So we have a starting coordinate in terms of frequency and level. We know what the slope is, and we know the number of octaves. So now we know what the total decibel change is to go from this plateau to this final breakpoint amplitude there. Now, I'm going to show you a slide in a couple of slides that goes over in more detail the dB formulas, but I'm just going to show you a preview now. For G squared per Hertz type calculations, the delta dB, that's the change in decibels, is equal to 10 log, and this is a base 10 log, times A over B. And A over B would just be 2 G squared per Hertz levels in this case. And if we do this calculation, we find that the final breakpoint is at 2000 Hertz is 0.007 G squared per Hertz. So think of this as being 007 like in the James Bond movies. Now, if we go to the vibration data signal package, and this is the main package we're running in the series of course units. It's up to version 4.6 now. One of the options we have is Power Spectral Density, and we can calculate an overall RMS value. So I'm going to begin the signal analysis. And let's see, what does this do? This script calculates the overall level of a power spectral density, and this assumes that the power spectral density is in log-log format, as would be the case in a test specification. The input array must have 2 columns, frequency in hertz, and amplitudes units square per hertz. Typically, units will be in G. So we either have to have the numbers for, and this will be the coordinates for our PSD, in RA in a MATLAB array or an external ASCII text file. And I have these points already in a text file. It's called navmat_spec.psd. And this will be an acceleration input where the time history has amplitudes of G. And we're going to plot from 20 to 2000 Hertz, which are the upper and lower frequency limits of our specification. So we calculate that. The first plot that comes up is a cumulative RMS plot, and we're going to ignore that for the time being. And here's our test specification. This is the navmat curve. And according to this software program, the overall level out to 2 decimal places is 6.06 GRMS squared. So that's the overall level of the specification. And we can also go to just our MATLAB command window here, and we can see some other information. We can see, okay, here's the GRMS value, and we're assuming that the mean value is equal to 0. So we're assuming that GRMS and standard deviation will just be the same values. So the 3 sigma value, which is 3 times the standard deviation, is 18.2 Gs. Then we also can take a look at the velocity and the displacement. And this could be important, for example, if we're trying to determine how the test specification will be for our shaker table, because our shaker table is going to have stroke limits for displacement, and shakers also have limits for velocity, acceleration, and other metrics as well, other parameters as well. So those are some of the things we can do with that utility. And actually, I want to back up a little bit. I want to show you one other thing we can do within the vibration data software. If you ever need to do some breakpoint calculations where we have slopes and points, we can go to the option here where it's going to be under miscellaneous, and it's dB calculations for log-log plots. And this is going to be at separate frequencies. So let's go back and kind of fill in a step here, and let's verify that the final breakpoint really is 007 per the software. So we're going to have a g squared per hertz level, and we're going to find the new coordinate given a slope and one coordinate. So this known breakpoint here is 350 hertz with 0.04, and the slope, dB per octave slope from the lower frequency to higher frequency is going to be -3, and the new coordinate is going to be 2000 hertz. And as we do that calculation, we see that at 2000 hertz, the final breakpoint to 3 decimal spots is 007 g squared per hertz. Then we also get some information on the slope. Now, let's round that the second number to -1. This means on our log-log plot, the -3 dB per octave slope would be -1. So it would just be a diagonal line. And that you know, assume that the decades in our log-log plot have the same you know, length and width, or the same for our height and width for our decades is the same. It would just be an angle sloping downwards at -45 degrees in that case. And then these numbers correspond to what we've already calculated, the octave span and the dB change. So within vibration data GUI package, there's just a couple of utilities that you can use to do these sorts of dB calculations and extrapolations and finding the breakpoints, as well as calculating the overall RMS values. And I actually want to go back and explain just a little bit more about what went on within some of those calculations. So our PSD specification almost always is in log-log format. And to do that calculation that we've just performed to calculate the 6G RMS level, we have to divide this up into 3 segments. So we're going to calculate the GRMS squared area for each of the 3 segments, and then the overall level, is the square root of the sum of the squares. So back when you were in high school and you were learning about Cartesian coordinates and XY plots, you learned that the slope of a line, or a line, could be characterized, a straight line, as y is equal to mx plus b, where m was the slope. Well, for log-log format, we have something that's a little more complicated here. So we have to consider the equation for each of the 3 line segments in our PSD function for our navmat level. So the PSD level, let's just call that y. Y is a function of frequency, so frequency is going to be the independent variable. And that's equal to this term here. We've got in the numerator within the brackets y1, so that's a known or reference, a reference PSD level, a g squared per hertz level, divided by the frequency corresponding to that reference PSD with a exponent of n. I'll explain n in the next slide. And then that's times the independent variable frequency f, which is also raised to the power of n. So our reference coordinate, or our starting coordinate, is f1, y1, so that's frequency 1, and the PSD level 1. That's where we start out. Now, what is that n slope? What is that? Well, our n slope, that exponent here, is the slope between 2 coordinates. So here we have log. This is base 10 log. So in our numerator term, we have an argument where we have the PSD at point 2 divided by the PSD at point 1. That's in terms of that corresponding g squared per hertz levels. Make that the argument, take the base 10 logarithm. Then we divide in the denominator. We have frequency 2 divided by frequency 1. So we have the reference frequency 2 divided by the the new frequency 2, typically f2, divided by the reference frequency f1. Take the logarithm of that, carry out that division, and that's how we calculate the slope in a log-log plot. So knowing what the slope is and knowing what that previous equation is for the straight line segment in the log-log plot, we can do an integration. So we have to carry out an integration, a separate integration for each of the 3 segments. So as we go back to here, we're going to calculate we're going to do the integration for this first segment. Now for the second segment, that's really easy to calculate because it is a flat line. And then we have our third segment here. So here's our integration formula. So think back to calculus. So we plug in our equation for y here. We're integrating with respect to frequency, but between a starting frequency and an ending frequency for that given segment. So this is how we get the GRMS squared area for that segment. And it turns out for this integration formula, there are 2 separate equations to evaluate it, and those depend on what that n value is. Because if you remember from calculus, if you have n to the minus 1, so you have 1 over f in that case, that's going to be a special integration rule. So here we have our 2 cases. So we have our area for our segment 1. And I'm not going to call out all those individual terms. I've actually have a paper posted in my blog that you can go back and review to get more details. But if n is not equal to minus 1, then this is the equation for calculating the actual area. Or in other words, this is the equation for evaluating that integral. Now for the very special case where n is exactly equal to minus 1, then we have this term with a natural logarithm function. And it turns out that minus 1, slope of n equal to minus 1, that's minus 3 dB per octave. That's what that special case is. Well, if you go back to this plot here, it just so happens we have a special case of minus 3 dB per octave. So somewhat infrequent, but we do occasionally run across that slope case. So for our problem at hand of calculating the overall GRMS level for that Navy PSD specification, we need to make use of both of those formulas. Now, once we get the GRMS squared areas for each of the 3 segments, then the overall level, I'll call that L, is the square root of the sum of the squares. So M is the total number of segments, so we just sum up the GRMS squared areas for each of the 3 segments, square root of the sum of the squares, that's our overall GRMS value. So it'd be a good exercise if you're so motivated. You might want to just write up your own MATLAB script or program for calculating the overall GRMS levels. But if you do that, then please account for the fact that slope may or may not be equal to minus 1. And of course, you're also welcome to just use the vibration data GUI package for doing that calculation as well. Okay, let's talk about dB differences between 2 levels. We've already talked about this in a previous slide. So let's take two levels. These will be g squared per hertz levels. One is A and one is B. So the dB difference between those 2 levels is equal to 10 log, so base 10 log, A over B. And what's interesting about these sorts of logarithmic calculations, if A is greater than B, then this is going to be a positive decibel value. But if we switch those around, it's going to be the same number, only the polarity will change. So if we have A over B is 6 decibels, then B over A is going to be minus 6 decibels. It's kind of interesting how that works out. Now, if we have 2 amplitude parameters C and D, they're both in units of G, or GRMS squared, it's the same formula except that this scale factor here changes from 10 to 20. And a good way, this is how I think about this when I'm trying to remember which I should use, is that you always need a 2. So if your 2 is an exponent applied to your amplitude metric, then that takes care of the 2. You just use 10 log. But if you do, if your exponent for your amplitude metrics is just 1, then you have to apply the 2 here out in the scale factor. Now, we're also going to, later on, we'll be doing acoustics and a few other things where we take a look at decibels as well. And we'll use these formulas again. Well, how do these apply to our PSD functions? Well, another way they apply is when we're dealing with test and design power spectral densities, one of the common tasks we have is to change that level. We might have to add a margin. We might have to raise the level by 3 dB. Or add it by 6 dB, increase it by 6 dB. And that could be due to we need to add some statistical uncertainty margin, we need to apply a safety factor, who knows. Sometimes, for example, we have, in aerospace, we have acceptance testing and we have qualification testing. And the qualification level is to be 3 dB higher than the acceptance level, or maybe 6 dB higher than the acceptance level. Or for the case of launch vehicles, we have range safety. And the range safety officers might say, okay, you need to have a margin of 10.5 dB, for example, because there's extra conservatism needed. So let's just do an example here. Let's say we have a power spectral density level and we add 6 dB. Well, if we add 6 dB to that power spectral density level, that is going to double the GRMS level. And the G square per hertz magnitudes will quadruple. And conversely, if we subtract 6 dB from a power spectral density, the overall GRMS level decreases by 1/2, and the G square per hertz values decrease by 1/4. And we can actually do these sorts of calculations using the vibration data GUI package. Let's go back to dB calculations for log-log plots. And we're going to do coordinates of the same frequency. And I'm just going to simplify this a bit. Let's say we have a G square per hertz level, and it's just 1. I'm just going to put amplitude 1. So we got 1 G square per hertz. Okay, let's find a new level given a dB difference in one level. So what happens if we add 3 dB to G square per hertz number? It doubles. Okay, what if we add minus 3 dB? Goes down by 1/2. What if we add positive 6 dB? Goes up by 4. And when I say goes up by 4, there's a little bit of rounding off going on there. And let's not get too hung up on the rounding off. What if we subtract 6 dB? So then we have 1/4. Okay, and then for GRMS value, what if we add 6 dB to our GRMS value? We get 2 Gs. And actually, I need to go back and fix this a little bit and say GRMS, but you get the idea that the GRMS level is going to double if we add 6 dB. So you can play around with this yourself. Who knows, you might have some odd case like, okay, we've got to increase 10.5 dB. Well, then we're going to go up by a factor of 3.35 in terms of GRMS. So this is a utility. You're welcome to use it, and I hope that you will get some use out of that. Okay. So how do we actually calculate a power spectral density? We've been talking about specifications. How do we actually calculate a power spectral density if we have a measured time history? So we're starting with a time domain signal. There's 3 methods that we can use. And the first method we're actually going to cover later on when we get to filtering. But we can measure the RMS value of the amplitude in successive frequency bands where the signal in each band has been bandpass filtered. And the number 1 method there is a wonderful educational method, and it's also an old school method. back from measurement days when, before we had digital data acquisition systems. And it has its own elegance, but we'll be covering that later on. But imagine if we did a bandpass filter from, say, 10 hertz to 20 hertz. So we bandpass filter our data, then we calculate the RMS value within that band. Then we square that RMS value, so we have RMS squared. Then we divide by the bandwidth. Now if we go from 10 hertz to 20 hertz, that's a 10 hertz difference, or 10 hertz bandwidth. So we would take our GRMS squared divided by that bandwidth. The second method is we can take the Fourier transform of the autocorrelation function. This is the Werner-Khinchin approach. That's a very esoteric method, and if you'd like to write your own MATLAB script to do that, you're welcome to do so. But we're really not going to cover that in our class. But maybe later on we'll talk about autocorrelation functions. But the second method here, that's more for the PhD people that have maybe a greater appreciation of theory than we might have in engineering. And then the practical method, when we have digital data acquisition systems and digital data, is to take the limit of the Fourier transform times its complex conjugate divided by its period t as the period approaches infinity. And the method we're going to do in this class is going to be a takeoff from this third method. Now we're back to this whole situation of the mathematician's world and the engineering world. And as engineers, we do not have an infinite period of data. The data we measured might be 10 seconds or 2 minutes or 10 minutes, it just depending on what we're measuring. But we have finite duration time histories. So we're back again to what would the textbook say? Well, mathematicians actually spend little time, if any, doing power spectral density functions. They're more involved in theoretical abstractions. But at such times as they do take a look at power spectral densities, they would give this sorts of formulas. So we're back to our mathematician world, Fourier transform, which would be amplitude time. So let's just say amplitude is g and time is seconds. So we have g seconds times g seconds. Well, that gives us g squared seconds squared. We divide by the duration t, so we divide by seconds. We're left over with g squared seconds, and we can convert that to g squared per hertz. So that's what the mathematicians would have us do. Well, in engineering, we have our modified set of Fourier transforms. So I'm showing our modified set of engineering transforms, Fourier transforms here, and I'm using the letter G here, and these have a dimension of amplitude. So our Fourier transform gives us amplitude, and actually what it gives us is complex amplitudes. So if we take the complex amplitude, the magnitude at each frequency, or amplitude at each frequency, times its complex conjugate, and we can divide by delta f, as delta f goes to 0. Now, delta f is never going to go to 0 because that would imply an infinite duration. For practical purposes in engineering, delta f, it might be 1 hertz, it could be 5 hertz, maybe a little higher than 5 hertz, maybe a little lower than 1 hertz, but typically it's going to be in that ballpark. And we're just going to live with the fact that it's a non-zero delta f, and that will suit us just fine. We'll be in good shape for something that's practical to design and test to. This is going to be one-sided. So let's say that these Fourier magnitudes are acceleration in g's. So in this case, we're going to have g squared per hertz. Now, as you recall, there's actually a few little intermediate steps that we have to do as well, or additional steps, because the direct output of our Fourier transform is g peak levels. And we actually have to convert those peak levels to RMS values by dividing by square root of 2. Looks like I got a little typo there, but you get the idea. We have to divide our g peak levels by the square root of 2 and our Fourier magnitude to convert them to RMS values. and then we can do that calculation. Actually, I don't have a typo there. Must also convert from peak to RMS by dividing by 2, square root of 2. Okay, we're good to go. Okay, a few things about some of these formulas that are important for dynamic data acquisition and analysis, and for Fourier transforms, and for power spectral densities. We're going to take our whole period. When I say the whole period, that's the whole duration, t. And that's equal to n times delta t, where n is the number of samples and the time function in the Fourier transform. Obviously, we're dealing with digital data here. T is going to be the record length or duration of the time function. And delta t is going to be the time step. So it's actually the inverse of the sample rate. So that's a sampling formula there. And there's another one that's very important. We've talked about this before. And this is that our delta F resolution, our frequency resolution, our frequency step, or the spectral bandwidth, or frequency increment, however you want to think about this, is going to be equal to 1 over t, where t is the total signal duration. Now, another way to think about this is consider a sine wave with a frequency such that one period is equal to the record length. This frequency is the smallest sine wave frequency which can be resolved in our Fourier transform. So let's say our duration is 10 seconds, and we have exactly one cycle of a sine function over 10 seconds. Well, that would have a frequency of 0.1 hertz, because it would be 1 over 10. So we have, in other words, we take a 0.1 hertz sine function, plot it for 10 seconds, we get exactly one cycle, and that's the smallest frequency our Fourier transform can resolve. It is also the frequency increment within the Fourier transform. And delta F is going to be fixed for Fourier transform calculations. Now, what I'm going to tell you is just to get through this next couple of slides, I'm going to say when we take a time duration and we take a Fourier transform of that time duration, we're just going to take a single Fourier transform for that whole time duration. And that's going to force the delta F to be 1 over t. Now, some of you are thinking, oh, yeah, but a couple of webinar units ago, we covered waterfall FFTs, and we found that we could take a time segment at a time duration and divide it into smaller segments and calculate an FFT for each segment. Yes, we did that, but just momentarily kind of set that aside, and let's just pretend that given a measured set of data, we can only take a single Fourier transform, and we're going to have delta F is equal to 1 over t, where t is the entire duration. Well, it turns out for our power spectral densities, we have some more leeway, we have some more flexibility, and we can alter what that delta F is. And what we're going to do for our power spectral densities is we're going to divide the total time duration into a series of shorter segments. Now, the delta F parameter is linked to the number of statistical degrees of freedom. And statistical degrees of freedom have to do with chi-square distributions, and I'll explain that a little bit later. The reliability of the power spectral density data is proportional to the degrees of freedom. So that has to do with the confidence integrals, the confidence intervals. And it turns out that the greater we make our delta F, the greater the reliability. And what we'll see later on is that the wider delta F is, that it tends to smooth out the power spectral density data. And when we smooth out the data, then we get a better reliable estimate of what the PSD level is within a band. More about that coming up in the next couple of slides. So the statistical degrees of freedom parameter is defined as degrees of freedom equal 2BT. Well, DOF, the statistical degrees of freedom, DOF represents the number of statistical degrees of freedom. B is the bandwidth of an ideal rectangular filter. Now, when I say ideal rectangular filter, I think of that as being a rectangular window. And you recall from a couple of webinars ago, we talked about Hanning windows versus rectangular windows. And what I told you is a rectangular window is equivalent to no window at all. In other words, we just leave the data unmodified. And it turns out that that bandwidth, B, is going to be equal to delta F, assuming an ideal rectangular filter. Well, delta F is 1 over T. So if we substitute delta F, or 1 over T, for B, we find out that the number of statistical degrees of freedom is equal to 2, because BT is always 1. So degrees of freedom is always equal to 2. So for this a little bit contrived example, I'm saying for a Fourier transform, we always get 2 statistical degrees of freedom. But I'm also telling you the more statistical degrees of freedom we have, the more reliable estimate we get of the PSD levels. So how can we resolve all that? Well, what we can do with power spectral density functions is that we can take that entire time duration, divide it into smaller segments. Each segment has 2 degrees of freedom. So we get 2 degrees of freedom per segment. So the total degrees of freedom, total number of degrees of freedom is then equal to twice the number of individual records. But the trade-off, the penalty, is that the frequency resolution widens as the time record is subdivided. And that widening of the frequency resolution can either be a good thing or a bad thing, it depends. And one of the potential consequences is if we have narrow spectral peaks, they might become smeared as the frequency resolution is widened, which may or may not be a good thing. So it's really good to take a look at this in terms of an example. So I have, for this example at the top there, 4,096 samples taken over a 16-second duration, and we will be using a rectangular filter. Well, it just so happens that 4,096 is conveniently one of those 2 to the nth power type numbers where n is an integer. So with 4,096 points, we can do a fast Fourier transform. So anytime we're going to do a power spectral density calculation, we need to apply some critical thinking skills and determine how we're going to process this data. And this is, I'm going to give you a little soapbox type comment here. If you're already using a power spectral density software, and it's just a turn the crank type software, and you are not prompted for this type of a decision table here, that's not the way to go. And eventually, when we run the power spectral density software or function that's included in the vibration data GUI package, you will be required to go through this sort of decision processing process here as to how to perform the power spectral density calculation. So this top row of numbers here, we have the number of records, 1. So we're going to take all 4,096 points. 16-second period for the total record. The frequency resolution is going to be 1 over T. Well, it's going to be this T here, so we have 1/16. So in other words, our delta F is going to be 1/16 of a hertz. The degrees of freedom per record, it's always going to be equal to 2 regardless. So 1 times 2 is equal to 2. We get a total of 2 statistical degrees of freedom if we take all samples. Well, that might be okay. So this would be the power spectral density, exactly 1 power spectral density taken for all 4,096 points. Now I'm going to skip down a couple rows and say, what if we take that 16-second record and divide it into 16 segments? Well, each segment is going to be 1 second long, because 16 divided by 16 is equal to 1. 4,096 divided by 16 is 256. So each 1 second long record will have 256 samples in it. Our frequency resolution, our delta F in hertz, is going to be 1 over 1. We always get 2 degrees of freedom per record. So we have, in this case, 16 records times 2 degrees of freedom per record is equal to 32 total statistical degrees of freedom. Well, what does this all mean? It means if we go through this process and we divide our total duration into 16 segments, we get higher degrees of freedom. So in terms of confidence intervals and reliability, we're more confident in the reliability of our PSD level going this route as opposed to our first choice there. Well, the trade-off, and this may or may not be a good trade-off, is that our delta F is going to widen, because here we get a frequency resolution of 1/16 of a hertz. Here our resolution is 1 hertz. So what's the correct answer for a given set of data? That depends. It depends on what the goals are, the objectives. If we're doing a shaker table test, and it's a broadband random test, a base input power spectral density to an avionics component, typically we would want our resolution to maybe be about 4 hertz, maybe a little higher, maybe a little lower, sometimes 5 hertz, maybe sometimes 10 hertz. So in that case, for our 4,096 points, this final row here might be a good choice. And actually, we could have added several rows to this as well, but decided to cut it off after 64 records just for brevity. But a delta F of 4 hertz would be typical for shaker table testing. And the reason we would want to do this is because we want to smooth out the data so we can demonstrate compliance within tolerance bands. Because on the other hand, if we had 1/16 of a hertz, we might show that certain spectral lines exceeded the upper tolerance bands, or certain spectral lines dropped out below the lower tolerance bands. And if that happened during a shaker table test, then that data would go to a quality control person who may or may not understand the finer points of random vibration testing, and it might cause some unnecessary consternation or some waivers or some paperwork. And we want to avoid extra paperwork, extra consternation, and we just want to show a nice, happy, smooth PSD plot for a shaker table test to show compliance for our specification. Well, what if, on the other hand, we were doing a modal test, that's M-O-D-A-L, modal test, and we were trying to identify a lightly damped, very low frequency spectral peak? Well, if we're trying to identify a very lightly damped, low frequency spectral peak, we may need this extra frequency resolution, and if it's a distinct peak, then we might be willing to sacrifice some degrees of freedom because we're not trying to show energy over a band, we're just trying to find individual peaks, well-defined, almost sinusoidal type peaks. Then this first case would most likely be the best case to go. So the answer is it just really all depends. Are we trying to identify spectral peaks that are narrowband or sinusoidal peaks superimposed on broadband random vibration? Or do we have something like white noise or some broadband shaker table type vibration? It all depends. What if we have measured field data? And of course, there are some cases where some intermediate choice might be appropriate. In some cases, if we're taking a power spectral density of measured data, we might actually want to try several different choices just to see what makes the most sense. And really, to a large degree, the final choice depends on engineering judgment. And I know engineering judgment can be a highly emotional phrase. That there are people out there that believe everything should be turn the crank, and if you buy a Big Mac in San Diego, California, it should be the same Big Mac that you could buy in Augusta, Maine. But I don't like cookie cutter analysis. I just don't. I like engineering judgment. Okay. So in summary, what we can do for our power spectral density calculation is we can break our overall time history into individual segments, and we do this to increase the statistical degrees of freedom. Now, as you recall, we had the potential error source called a leakage, and despite what that bullet says, we can never really prevent it, but we can suppress it. It actually could be. We can actually prevent leakage altogether if we have a pure sine function and we take an integer number of cycles. But for the generalized cases, especially for random vibration, we can never fully eliminate leakage, but we can certainly reduce it by applying a Hanning window. Well, the problem with Hanning window is that it takes away some of our data. And when we apply the Hanning window, we reduce the degrees of freedom. And even though we take our Hanning window data and we multiply by that square root of 8/3 normalization factor, the fact is we're still losing some degrees of freedom when we do that. So our workaround there is we're going to use something called overlapping, and we're going to typically do a 50% overlap when we take these segments. And when we do that, we recover 90% of the degrees of freedom with a 50% overlap. That's sort of as a rule of thumb. So let's say we have our original sequence here, our time history sequence. And I'm not showing what the units are, X and Y. It doesn't really matter for this case. And let's say we're going to divide this into 3 segments because we want to pick up some extra statistical degrees of freedom. So this bottom plot here shows what happens when we apply the Hanning window. So the Hanning window is kind of like a bell-shaped type curve. And we also apply that square root of 8/3 normalization factor. And you can see we're losing some data at the beginning and end of each individual segment. So we're losing some useful information as we try to accumulate degrees of freedom and apply the Hanning window. So that's a problem. Well, and the way we solve that problem is actually, as I mentioned earlier, what we're really going to do is we're going to take 5 segments, not 3, and these will be 50% overlapped. So we're going to apply the Hanning window to each of the segments there with our 50% overlap, and we can recover 90% of the lost statistical degrees of freedom. Our next step would then be to take a PSD of each individual segment, and then the final PSD, the overall PSD, is just going to be the average of the 5 individual PSDs. And since it's RA and G squared values, we can average the PSD G squared per Hertz values. And that's how we do vibration processing in terms of calculating power spectral density functions, particularly for shaker table testing, and in other contexts as well. Okay, and that actually finishes up our slides for this unit. I'm trying to hold this down to roughly an hour or so, and in our next unit we're actually going to calculate some power spectral densities and take a look at some of the trade-offs as we change the number of segments and delta F and so on, and that will be within the vibration data GUI package. And just to show you a few things, oops, got some personal stuff up there you probably don't need to see. Let's go to our vibration data blog. So if you go to www.vibrationdata.com, scroll all the way to the bottom for the blog link here. So let's type in the word webinar. And for Unit 11, Power Spectral Densities, I have the PowerPoint slides there. And eventually I'm going to have this very audio visual recording will be posted here as well. Then I've got a couple other things. I've got a link to the vibration data signal analysis package. I've got a couple of reference papers. The first one is integration of the power spectral density function, and that actually goes in a little more detail about those integration formulas that I showed you earlier. I also have one on statistical degrees of freedom, and this has to do with those confidence integrals and that chi-square distribution. We'll take a look at that here momentarily. Then I also have one giving more information on the power spectral density units, G squared per Hertz, which is really GRMS squared per Hertz. And this one is actually going to show you the bandpass filtering method that we're going to cover later on. But let's go to statistical degrees of freedom. And I'm not going to go over this verbatim. You can kind of read this on your own. Some of the information in this document we've already covered in our slides. So I'm just sort of scrolling through this. It's got that same table we just took a look at earlier. So for our chi-square distribution, and I do not have a PhD in statistical theory. So I've had one college course in it, but to really understand chi-square distributions, I would have needed a second college course in statistics. But what it is, it's a distribution of squared values. So when we're dealing with g-square per hertz values, those lend themselves very nicely to a chi-square distribution, which is a distribution of square values. It's well suited for stationary random signals, but if we have non-stationary signals or deterministic signals like sine functions, then it would not apply very well, if at all. Okay, and then there's different ways we look at the formulas, looking at with the chi-square distributions. We have a sample standard deviation value S, and then there's the true population mean square amplitude, which is going to be sigma squared there. So think of sigma squared as being like the variance, and then that's equated to the chi-squared distribution value divided by the degrees of freedom. So if we consider a mean squared value S squared, this is the measured sample value for time t. The true mean squared amplitude, sigma squared, will lie within a confidence interval determined by this relationship here. So the chi-squared distribution helps us to establish what the confidence interval is. And you can kind of go through some of these at your leisure if you're interested more in the theory. So here's an example here. What if we have so if we have to set, what's our percent for our confidence interval? So if let's say we have the bounds for the 95% confidence interval, and those bounds are on S squared here. So if we have 8 total degrees of freedom, we have confidence bounds as shown here. But if we increase that all the way up to 64 degrees of freedom, then what we find is that those confidence bounds narrow. Then there's a related parameter called the standard error. So the higher our degrees of freedom become, then the narrower our confidence intervals become for a given percent confidence level. And much beyond that, you're going to have to dig into this yourself. And because I'm showing this directly from my WordPress blog, and some of those fonts are messed up. But if you download the PDF document yourself and just look at the PDF viewer, then they'll all get cleaned up. So again, I'm not pretending to be an expert on statistical theory, but what I do know is that the more degrees of freedom we have, the more confident we are in the reliability of our data. And that's going to be it for today. So hope you've enjoyed this material, and you can make use of those MATLAB scripts that we ran for calculating the overall RMS levels and doing dB and dB per octave slope type calculations. So if you have any questions, you're always welcome to send me an email. And you can contact me via email at tomirvine@vibrationdata.com. Just show that for you here. It's Tom at vibrationdata.com. Please send me an email at tom@vibrationdata.com if you have any questions. Thank you and have a wonderful day.